When you send text messages, you have the expectation that everything you send is private and can only be read by the person you send it to. The primary way companies promise that level of privacy is through end-to-end encryption.
Text messages typically use symmetric encryption, meaning the same key is used to encrypt and decrypt messages. This key is commonly a 256-bit long string of zeros and ones that is used along with an encryption algorithm to encrypt a message. This encrypted message is then sent over the internet to the recipient, who has an identical key to decrypt the message.
The issue with symmetric encryption is that typically, the protocol that distributes the keys must send a copy of the key to the recipient. This is primarily done using asymmetric encryption, where messages are encrypted using a public key and decrypted using the corresponding private key. The private key uses two prime numbers to decrypt the data, while the public key, which is the product of those two numbers, is used to encrypt it. Asymmetric encryption is currently secure because factoring large numbers is extremely difficult for classical computers to do. However, quantum computers will be able to solve this problem efficiently, and a more secure method of key exchange will be necessary.
In this video, we'll talk about one such method, BB84, a quantum key distribution protocol, and why it's more secure than classical key distribution protocols. But before we can talk about BB84, we need to introduce some quantum computing fundamentals.
In quantum computers, qubits are the smallest unit of information. Physically, they can take a variety of forms, such as photons, electrons, neutrons, or ions. Like classical bits, qubits can be in the 0 or 1 state. But, interestingly, they can also be any state in between 0 and 1. This in-between state is called superposition.
Qubit state is typically visualized on a diagram called a block sphere. The 0 state looks like this on a block sphere, and the 1 state looks like this. The qubit is in a superposition if the arrow points anywhere else. The symbols enclosing the 0 and 1 follow Dirac or Braket notation, where these are called kets. Two other important states are the plus state and the minus state.
When a qubit is in superposition and we measure it, the superposition collapses, and the qubit is detected as either being in the 0 or 1 state. The probability of the state collapsing into the 1 state when a qubit is measured follows this equation. If we plug in the 90-degree angle formed between the 0 state and any point on the equator of the block sphere, we see that all of these states have a 50-50 chance of collapsing into the 0 or 1 state.
The default state of a qubit is the 0 state. Whenever we want to alter the state, we use quantum logic gates. The single qubit gates involved in BB84 are the Hadamard or H gate and the X gate. If we applied the H gate to our qubit, it is brought into the plus state. If we apply the H gate again, it is brought back to its original 0 state. The X gate performs a 180-degree rotation around the x-axis. So, from the 0 state, we can use the X gate to bring our qubit into the 1 state. From here, applying the H gate brings us to the minus state. If we apply the H gate once more, the qubit is brought back to the 1 state. Because of phase, the H gate applied twice consecutively will always return the qubit to its original state.
This is one reason the block sphere is shown as a 3-dimensional sphere instead of a 2D circle. This third dimension is created by phase. When this state is at any point on the same z-axis, the probability distribution of its state when the superposition collapses is unaffected. However, the rotation an H-gate would apply on the state is affected by phase.
Now let's take a look at an important multi-qubit gate, the CX or controlled X gate. The CX gate acts on two qubits, the control qubit and the target qubit. If the control qubit is in the 1 state, the CX gate applies an X gate to the target qubit. But if the control qubit is in the 0 state, it does nothing to the target. If the control qubit is in superposition and the target qubit isn't in the plus or minus state when the CX gate is applied, the gate will entangle the two qubits. When qubits are entangled, their states are connected, so measuring the state of one qubit gives us information about the state of the other.
To see entanglement at play, let's create a circuit that uses the CX gate. We'll begin with 2 qubits in the 0 state. Then, we'll use an H gate to put qubit 0 into the plus state. If we now apply a CX gate to the circuit, where qubit 0 is the control, since it's in superposition, it will randomly choose whether to be in the 1 state or the 0 state. When the control qubit is in the 1 state, an X gate is applied to the target qubit.
To visualize this, let's split our diagram in two, where the top shows a circuit where the control qubit picks the 0 state, and the bottom shows a circuit where the control qubit picks the 1 state. Keep in mind that the CX gate does not act as a measurement to the control qubit, because while measurement breaks superposition, destroying entanglement, the CX gate does not break superposition, and instead creates entanglement.
But how do we know the two are really entangled? Right now, they seem to have just been conveniently put into the same state. Let's apply an H gate to qubit 0, bringing the top one in the 0 state to the plus state, and the bottom one in the 1 state to the minus state. Now, let's apply the H gate to qubit 1 and measure both. Since the qubits are in a superposition state, where they each have a 50-50 chance of collapsing into either the 0 or 1 state, we should expect a 25% chance of each 0, 0, 0, 1, 1, 0, and 1, 1 state. Let's run our circuit on a quantum computer and see the results of our measurements.
Surprisingly, we only get 2 results instead of 4. That's not what we expected, but because of entanglement, at the moment we measured the first qubit, both superpositions collapsed, and the other was forced to flip to the same state.
It is important to note that the only reason we can visualize the qubit states this way is because we know the beginning state of the qubit and every gate that is applied to it afterwards. Because we usually don't have all that information, it's more common to use quantum circuit diagrams to visualize multi-qubit circuits. Here, each row represents a different qubit, and each figure represents an operation. These are H gates, this is a CX gate, and these are measurements.
Now that we have a working understanding of some quantum computing fundamentals, let's talk about BB84. BB84 leverages the advantage of superposition to ensure that keys cannot be successfully discovered by any attack, at least not without the communicating party's knowledge.
Let's say these two parties are Alice and Bob, and they want to share encryption keys using BB84. Let's break it down into a 7-step process.
Step 1. Alice creates a string of qubits, and for each qubit randomly picks whether or not to apply an X gate to put it into the 1 state.
Step 2. Alice generates a basis string with 1 basis per qubit. The X basis applies an H gate, and the Z basis applies no gate. Then, Alice applies each basis to its respective qubit.
Step 3. Alice physically sends her qubits to Bob via a quantum channel. For example, if the qubits are photonic, which means that they are light particles, she could send them through a fiber optic cable.
At this point, if Bob knew which qubits were in superposition, he could just undo the superposition by applying another H gate. However, Bob has no way of knowing which qubits Alice encoded in the X basis, so he must guess.
Step 4. Bob takes the qubits he received, creates his own random basis string, and applies a basis to each corresponding qubit. Then he measures all the qubits, giving him a string of bits.
If Bob and Alice apply the same basis to the same qubit, Bob will measure the correct bit value. However, if Bob chooses the wrong basis, the qubit will be in a superposition and collapse randomly into the 0 or 1 state. This means that Alice and Bob are guaranteed to get the same bit when they use the same basis. However, due to superposition, when they choose opposite bases, they have a 50% chance of getting different bit values. Because of this, Alice and Bob will likely have different bit strings at the end of this step. But for symmetric encryption to work, they need identical keys.
Step 5. Bob notifies Alice that he received the qubits, and they share their basis strings. Because there's a 50% chance that their bits are different when they use different bases, they must discard all the bits where they use opposite bases to guarantee that their bit strings are identical after this step.
Keep in mind, the process can always be restarted, so if something goes wrong, like if they discard too many qubits in this step, it doesn't actually matter.
In step 6, Alice and Bob verify that no one has eavesdropped on the quantum channel. This step only requires that they compare the first half of the remaining bit strings with each other. If the halves don't match, Alice and Bob can conclude that there was interference.
Finally, in step 7, Alice and Bob create their encryption key from the unshared half of their bit strings.
With this system, why are Alice and Bob always able to detect eavesdropper attacks? Let's explore this by looking at 3 ways a malicious third party could interfere with the quantum key distribution process: the measurement attack, intercept and resend attack, and entanglement attack.
Say an eavesdropper, Eve, is attempting to get a copy of Alice and Bob's key. There are 2 points Eve could exploit to get information about the key. The first point is the qubit transmission from Alice to Bob. The second is when they share basis information. In each attack, Eve uses the basis information to discard the same bits that Alice and Bob do during step 5. The only difference between all these attacks is how Eve intervenes during qubit transmission.
In the measurement attack, Eve intercepts and measures the qubits, then sends them to Bob. Bob proceeds with his normal steps and ends up with his own bit string. But why won't Eve get away with eavesdropping?
Once Eve intercepts the qubits, each can be in any of 4 states: the 0 state, the 1 state, the plus state, or the minus state.
When Eve measures the qubits, the superpositions are collapsed, and every qubit is now in either the 0 or 1 state.
Since each qubit is either in the 0 or 1 state, whenever Bob applies the X basis, he puts the qubit into superposition. They would normally both get the same bit value. However, because Eve interfered, when they compare their keys, they will have mismatching bits about 50% of the time they use the X basis. This will indicate that a measurement attack has been attempted.
The intercept and resend attack is similar to the measurement attack, but Eve adds a step. Before measuring the qubits, she applies random X or Z bases. Then, after measuring, she applies the same sequence of bases to the qubits and sends them to Bob. Why does this attack also fail?
Eve attempts to avoid detection by applying her bases before and after measurement, remembering that an H gate applied twice returns the qubit to its prior state.
Unfortunately, Eve forgets that measurement collapses superposition and notifies Alice and Bob of her eavesdropping.
Because of the interference, Alice and Bob will get different bit values half the time Eve picks a different basis than Alice and Bob, meaning that there will be about a 25% discrepancy when they compare at the end.
The entanglement attack is also similar to the measurement attack, but Eve switches measurement with entanglement. Since Eve now knows that measurement collapses superposition, which allows Alice and Bob to detect her, she thinks that entangling her own set of qubits with the qubit she intercepts from Alice should circumvent that obstacle. Since she now has qubits of her own, she waits until Alice and Bob share bases to apply hers, and throws away the qubits that Alice and Bob discard.
To explain why this attack also fails, let's take a look at the 2 possible circuits, assuming Alice and Bob picked the same bases. Without interference, the circuit diagram would look like this. Here, when the initial state is 0, the circuit should always measure a 0 state in both bases. With Eve's interference, why is that any different? Looking at the diagram on the top, we're reminded of a circuit we looked at to explain entanglement. Remember that when we then measure the qubits, they return the entangled 50%, 00 or 11 states. Since the CX gate alters the state of the intercepted qubit by entangling it with Eve's qubit, the final H gate brings the qubit into the plus or the minus state, meaning that when Alice and Bob compare their keys, they'll notice that half the time they use the X basis, they got different values.
In this video, we looked at quantum circuits and quantum entanglement with a CX gate. We used those quantum fundamentals to establish BB84 and explained why every attack, besides randomly guessing the key, fails.
While modern-day prime number-based asymmetric encryption does the job, who knows how long it will be until quantum computers will break it. Maybe not for another decade, but it will happen eventually, and we must be ready for it. Thanks for watching.